Good afternoon. This podcast is designed to teach you how to do thermochemical problem sets. In this podcast, I will demonstrate to you how you can solve for heat, work, mass, and also the specific heat of various problems. You will also learn about the indirect method and direct methods of how to solve for chemical equations. Let's begin with example 1. Looking at example 1, if burning fuel in a potato cannon gives 855 joules of kinetic energy to the potato and releases 1422 joules of heat from the cannon, what is the change in internal energy of the fuel? How we will begin this problem is simply by, as we say, we always begin with what? Writing our givens. So our givens are stating that heat of the potato is equal to 855 joules, and the work done by the potato is at 1422 joules, meaning the energy that has been released. So this is letting you know that some energy has occurred, and this is what was produced from that energy. We can also specify that we know that if you have one energy, E2 minus E1, you can also calculate the difference in the energy of the fuel being produced. And that unit should also be in joules, which is a unit of energy as stated previously in the course. So our conceptual plan would be to find the heat and the work for the potato and look at the heat and the work for the fuel. We would have to calculate the two and use the relationships we know between delta E, heat and work, to do that. So let's look at this closely. The relationships that we've stated thus far is that we can know about systems and surroundings, and we can also know about heat of systems and how they are transferred to the surroundings. Keep that in mind that this is transferable to work of the system and work of the surroundings as well. So let's divert back to what we learned about systems and heat transfer, where we can say heat of a system can be equal to negative heat of the surroundings, and the same would apply for work of a system being equal to negative work of surroundings. This also allows us to equate things such as endothermic and exothermic type of properties. Now, we can also form the relationship, as we stated from the first law of thermodynamics, that we talked about the change in energy can be equal to heat plus work. So what would the solution tell us? The solution, we would simply say that the heat of the fuel would be related to the negative heat of the potato. Again, we're producing fuel from a potato. So our heat of fuel, we would associate that to be basically the work that was being done by the potato on releasing this energy from the system. We would denote that as negative 1422 joules. Negative because it's saying in the problem that kinetic energy to the potato and releases 1422 joules of heat, meaning release should have a negative sign due to that work being released to the surroundings. Now, let's look at the work from the fuel, and we can also relate that work from the fuel will be equal to negative work of the potato. Again, we're burning fuel in a potato cannon that's giving off 855 joules of kinetic energy to the potato. Okay, so the work of the fuel will be equal to negative 855 joules. Now we would simply put both of these into the equation, plugging them in to make sure that we know that Q plus W would be. Keep in mind that all symbols must be applicable to each operation being done. So we state that something, since energy is being released or given off or burning, that negative value from that number has to be entered or plugged into the actual equation we're using. In doing that, we would basically say delta E is equal to Q plus W, Q being negative 14 negative 1422 joules, and that would be added to negative 855 joules of energy to produce the energy change of negative 2277 joules. Again, we're talking about internal energy of fuel, so our unit of joules would still be that in that format, and we check for the unit and the sign of these two problems to be correct. Moving forward, if we look at example 2, if the reaction produces 3.1 times 10 to the second joules of heat and the decrease in volume requires the surroundings to do 7.6 joules of work on the system, what is the change in internal energy of the system? Similar problem from example 1. However, we're looking at now something occurring more in a reaction, a chemical system, but we're still equating everything to internal energy. So we start off writing our givens where we know the heat of the reaction produces negative 310 joules and the work of the surroundings is equal to negative 7.6 joules. Again, we have a decrease in volume. This is why this 7.6 would have a negative sign. It's doing work on the system. We need to calculate the change in internal energy, which would be delta E. And how we would proceed, we would take our conceptual plan, look at work of the surroundings. We would now go about calculating work of the reaction, place it into the formula that we know of, the equation that we can relate to internal energy, being Q and work. If you add them together, they will produce delta E. So for the solution, we would simply take our work of our surroundings, set those equal to the negative work of the reaction, because again now things are changing in the problem as stated. So you have to go back and make sure we look at the work problem directly as it should be, and we place everything according to what is being produced or what is being released. That's how the negative signs come into play. So we can say W surroundings is equal to negative W of the reaction. We now can basically say, if we know the heat of the reaction was related to denoted as negative 310, if our work is still going to be negative W of the reaction, we can do negative and negative. That would give us the positive values between the two. And we would simply add up heat plus work, which would be negative 310 joules plus 7.6 joules, giving us a final answer of the change in internal energy to be negative 3.0 times 10 to the second joules. Again, we check our units for our signs to make sure everything is correct. Let's begin by looking at example 3. Example 3 states that we want to know how much heat is absorbed by a copper penny with mass 3.10 grams whose temperature rises from negative 8 degrees Celsius to 37 degrees Celsius. Now, again, we have to sort the information given by separating it out into our given column and the find column. What are our givens? We write those specifically, and we know that we have a mass of 3.10 grams. This is a copper penny. We also know that we have two temperatures. T1 is negative 0.0 degrees Celsius because it is the lower temperature and it's starting at that point. T2 is 37.0 degrees Celsius because it is the final temperature. The word problem states to us that temperature rises. So we can conclude from that statement that the final temperature would be 37.0 degrees C. We also know that the problem is asking us to find how much heat is absorbed by this copper penny. Now, how do we proceed with actually solving the problem? We have to, again, strategize from what we've talked about before, and we've also derived a few relationships that stated in class that if we know a few things, we can actually solve for heat in a system. We stated earlier that if we know the amount of a substance, if we know the sample's temperature and the temperature change, we could calculate the amount of heat that has been absorbed or released in the system. Given that we can also determine or find the specific heat of the particular object that's mentioned in the problem. Specific heats and heat capacities are generally given to us from a chart or an appendix in the back of a textbook or in a handout. Now, with that being said, we can now form the relationship or use a relationship that we know of that stated that Q is equal to mass times specific heat times a change in temperature. For the slides given here, C sub of S is relating to specific heat. So that is the subscript that these particular handouts use to specify specific heat. Now, how can you further confirm that? You can also divert back to the units that we went over in class that stated things about specific heat as well. So with that being said, we know specific heat, we know mass, we know T1, we know T2. However, we do not know Q, which is the heat, and we need to determine how much heat is being absorbed because we have a temperature change from -8 to 37 degrees Celsius. So with that being said, we can form the relationships to figure out what is the specific heat of a copper penny, and specific heat for a copper penny is 0.385 joules per gram. Using that information, we can now plug in the problem to actually solve for Q. First, we would take, to solve the problem, we would take temperature 2 minus temperature 1 to give us the delta T, which would be 45 degrees C. And we can now rearrange or solve for our actual problem, which would be Q equals M C of S times delta T. So we would now just plug in our givens to state 3.10 grams times 3.85, which is joules per gram degree Celsius times 45 degrees Celsius. As noted in the relationship slide that the typo of joules grams per Celsius was left off, but it is considered 0.385 joules grams per Celsius, joules per gram times Celsius, because it is specific heat. Now we would check our problem by making sure that our units cancel out, and it's all about the units because the unit for heat is in joules, so that would be our final answer, which would be 53.7 joules. If we continue on to example 4, we want to determine what is the unknown mass of Pyrex glass that is on a hot plate. The hot plate is initially set at 23 degrees Celsius. When the hot plate is turned on, it absorbs 1.95 times 10 to the third joules of heat, and the temperature rises to 55.4 degrees Celsius. Again, what is the mass of the Pyrex glass? That's what we need to find. So we have a few things to think about here and extrapolate from this problem. Again, you always have to sort your information by writing your givens. What's the first thing we do? We write our givens. We can take from this problem. We don't know the mass of the substance, so that is what we will need to find. We are given a temperature, which starts off at 23 degrees C. Again, use context clues. Initially, this is telling you this is T1. This is at the beginning. Now it says that this hot plate is turned on and we have an absorption of heat that is at 1.95 times 10 to the third joules. Again, that is our Q value. It is absorbing heat. That is Q, the variable Q. The temperature rises to 55.4 degrees Celsius, so that would be the final temperature, which would be T2. And again, we have to find mass. So we then look at these givens that we have and we plug into our brain, or we extract out what formula we could actually use. Given that we know Q, we know we can determine specific heat from a chart, or it will be given to us if we take an exam. And we can also calculate delta T. So with that being said, let's proceed with solving for the problem. So how will we begin with the solution? In the solution block, we simply know that TF minus T1, or T2 minus T1, would give us 55.5 minus 23, leaving us with 32.4 degrees Celsius as the change in temperature, or delta T. We now have to rearrange the heat equation to solve for M. We do that by dividing both sides by C of S times delta T, or specific heat times delta T. We divide those by both sides. That basically lets us know that mass will be equal to Q over C of S times delta T. We plug in the variables now and we do the math, which would be a division problem, and our units should cancel out because everything will be inverted, leaving us with the units of grams. So we would have 80 grams of Pyrex glass that would actually absorb 1.95 times 10 to the third joules of heat. Again, you have to check for your units to make sure that everything is right. Keeping in mind that if it looks like a math problem, you have to treat it as a math problem to make sure that all your units cancel out, such as they would if it was a fraction. I ask that everyone please look over all the examples in the packet using the play function of the PowerPoint presentation to make sure you can understand all the steps when it comes to solving various problems. Now we're going to continue with slide 10 that basically is going to talk about solving the strategies for solving thermochemical equations. It's very important that everyone realize that all of these thermochemical equations will have certain quirks to them. So it's important that you understand these fundamental rules or strategies on slide 10. So briefly, I'm going to just read through them, but I've highlighted some things to kind of stick out, and when we actually do examples of the problems, hopefully it will help you in knowing how to actually begin solving these problems. So the first thing to remember is that all stoichiometric coefficients, we always refer to them as number of moles of each substance. Now this is important, and it goes back to Chemistry 111 when we talked about the moles or the coefficients that were in front of each chemical reactant or each compound. Remember, those are very important. If you're new to the class, one of the things that I always make you do is you make a statement about a chemical reaction. So that way you know, for instance, there are 2 moles of H2O and it produces 2 moles of hydrogen gas plus oxygen gas. Those things are critical for understanding how certain stoichiometric properties, the role that certain stoichiometric properties play in actual chemical equations. That fundamental information is going to be even more important when we start solving these thermochemical equations because they play a key role in enthalpy changes. Keep that in mind. So the next point is that you have to remember is that when we reverse an equation, you're changing the roles of the products and the reactants, but more so you're changing the magnitude of the delta H in the equation. That means that the sign of the delta H would change. So although you have reactants on the left and products on the right, if something happens and we have to reverse the equation, that requires us to change the sign of the delta H. Third point is that if we multiply both sides of a chemical reaction by a number, something that we can easily do in math, but we're going to translate that same concept to chemistry or a thermochemical equation. Whatever we do to the chemical equation, we'll have to do the same to the delta H value. So that means if we multiply an entire chemical equation by 2, on the left side and the right side with the products and the reactants, we have to multiply the enthalpy value by 2 as well. Next point is that when writing thermochemical equations, we always have to specify the states of matter or the physical state. So that means if something is a liquid, such as H2O, or something is a solid, such as H2O solid, meaning it's ice versus liquid water. You have to make sure you specify that the state of matter or the physical state of each product or reactant, because that in turn does have an effect on the enthalpy changes. And the last point is that the enthalpy of substances increases with temperature, and enthalpy change for a reaction usually depends on a specified temperature. So temperature does affect basically enthalpy change because again we're talking about various heat flows. So we'll move on, and just to further expound upon what I just said, when we talk about enthalpy of a reaction, we're essentially studying the enthalpy change in a chemical reaction, and it is an extensive property. I also talked about this a few lectures back, so keep in mind that the more reactants you have, the larger the enthalpy change can be, because we're talking about things such as that are related on the magnitude, the amount of something. It's very quantitative, where when you talk about intensive properties, they are independent of certain things. They're not dependent on a quantity or a value. Now, by convention, we can calculate enthalpy change for the number of moles in a reactant as it is written in the reaction. So again, for a reaction that we may have C3H8, that's a gas, it's a combustion reaction. It's mixed in with oxygen, 5 moles of oxygen gas to produce 3 moles of carbon dioxide and 4 moles of steam. That would have an enthalpy change, delta H value of negative 244 kilojoules. That specifically would tell us that the delta H for a reaction for 1 mole of C3H8 or propane would be negative 2,044 kilojoules. That would pertain for 1 mole of the C3H8 versus the oxygen, which we would have to keep in mind about the 5 moles of the enthalpy change there, so that 5 moles of oxygen would actually change the value of that. So it would be 5 moles of oxygen to the delta H value of negative 2044 kilojoules versus 1 mole of just that C3H8. So that is how the moles of the substance, it will be taken into account when we talk about enthalpy of reactions in thermochemical equations. So let's continue on and look at example 5. We want to look at how much heat is evolved in the complete combustion of 3.2 kilograms of C3H8 gas. So combustion reactions are typically reactions where we have a substance or gas that is basically reacted with oxygen to produce carbon dioxide and water. The previous example from before. Again, let's start the problem by writing our givens. So that's our strategy. We begin by writing our givens. All we know currently is that we have 13.2 kilograms of C3H8. We need to find Q, which is the heat that is involved in the complete combustion. Q, it would be in kilojoules per mole, because you're actually looking at a particular compound, and that would actually look at that molecule. So the moles would play an important role in this heat factor, because it's looking at how many moles of, joules per mole of that particular substance. So what do we know that we can pull into this equation to actually help us solve it? All we can determine from this currently is that we know the mass of the compound. We know from kilograms we can go to grams. From kilograms we can go to moles, and then we can go to our energy value. So how will we actually proceed with these relationships? Guess what? These are all things we've learned in 111. Nothing's new here. What's new here is the way we think about the problem and how we approach the problem, and how we take those different items that we know of to orient them in a particular way to solve the problem. So what I'm saying is that all of this information we see now is nothing new. We're just learning basically how to solve a problem from things we've learned previously. We know how to convert kilograms to grams. We know how to basically use molar mass and how we go from grams to moles and things like that. And now we can incorporate a new energy, kilojoules per mole from our previous slide. So let's look at the solution. From the previous slide, we can piggyback off of that given information, where we determine that the joules energy produced from this combustion reaction was negative 2044 kilojoules. And simply we would start with our given value of 13.2 kilograms. The propane, we will multiply it by 1,000 grams to kilograms. Then we would divide it by the molar mass of the propane, and then using the enthalpy change per mole, which is negative 2044 kilojoules per mole, that would give us basically our final unit of kilojoules, which will be negative 6.12 times 10 to the 5th. Again, this is basically like a conversion problem, right? And we would make sure all our units cancel out, because at the end of the day, it's all about the units, and this would help us solve for this problem. So let's move on to example 6. So example 6 basically asks us to consider the following thermochemical equation for the combustion of acetone. Now, acetone is the main ingredient in nail polish remover. The reaction for this is basically C3H6O, that is our acetone. It is being combusted, so it's reacting with 4 moles of oxygen gas to produce 2 moles of carbon dioxide gas plus 3 moles of steam. So the delta H for the reaction is equal to negative 1790 kilojoules per mole. And basically what we want to know is if a bottle of nail polish remover contains 177 milliliters of alcohol, 177 milliliters of acetone, how much heat would be released by its complete combustion. So let's set up the problem by starting with our given. So there's a lot of information we have here, and we have to start extrapolating from this actual problem. What do we know? We know that we have 177 milliliters of acetone. We're also given an enthalpy of reaction value, which is negative 1790 kilojoules per mole. And we also have a density value that we can determine from a chart or an appendix that can be given to us as well, that states that density for acetone is 0.788 grams per mole. We want to find the heat. Basically, is how much heat is released from this combustion reaction in kilojoules, using the plan of taking what we know to find what we don't know. Okay, so we know we have milliliters of volume. Since we have milliliters of volume, roll back the pages. Let's divert back to, again, 111. Although it's not given to you per se, you can also find the density of something. Density is mass per volume. So what happens if we take the mass per volume and relate that to the given volume? That would allow us to solve for grams. Then we can, next step, we can determine the moles. Using moles that we've calculated, we can now insert our enthalpy value to help us solve for Q in units of kilojoules. So with that being said, we divert back to some relationships that we formed, basically to say that acetone has a heat of reaction or enthalpy of reaction that is negative 1790 kilojoules. We can also determine the molar mass from the compound, which is 58.08 grams per mole. Now we set this up as a simple conversion equation, starting with the volume, 177 milliliters, times the density, 0.788 grams per milliliters, keeping in mind that milliliters is in the numerator for the volume, and with the density formulation, milliliters would be in the denominator. We can next invert the molar mass of 58.08 grams per mole to cancel out grams from our density equation. And lastly, we can insert delta H of reaction to cancel out moles from our molar mass component to give us a final answer of negative 4.30 times 10 to the third kilojoules. Again, we go back and we check our units by canceling out the units in the numerator and denominator, and that will let us ensure that our units are correct and all our units cancel out. Again, thermochemical equations are useful, especially when we're starting to do stoichiometry, because you have to incorporate knowing about how to orient the various problems to cancel out, just like we've done in 111. So with that in mind, we would keep moving forward doing some other examples. I'm going to ask that you actually walk through the PowerPoint and play those examples yourself. I'm going to ask that you use the peer leaders during this week's PLTO session to further help you with the calorimetry problems and also look at the examples I provided. What I'm going to do now is I'm going to jump to slide number 18 and go over the method of Hess's law, which is basically an indirect method to help with studying the standard enthalpy of formation of compounds. So one of the things that you need to be mindful of when we talk about Hess's law is that it basically looks at When reactants are converted to products, the change in enthalpy is the same whether the reaction takes place in one step or a series of steps. So, what do we mean by that? The change in enthalpy for a stepwise process is the sum of the enthalpy changes of the steps. So, what we're going to show you now is basically over a process of steps, you can have various chemical reactions occur. When that happens, these steps of chemical reactions form an overall process of the compound you're looking for. And that overall compound that is formed basically has a delta H of formation, a standard enthalpy of formation. But the product is formed in a stepwise chemical step process. So stay with me now, and we're going to go through each of these steps. So relationships involving enthalpies of reactions or enthalpies of formations of how products are actually formed can be calculated using steps, chemical reaction steps. When you multiply the enthalpy of reaction, the delta H of reaction, by any factor, basically you do that throughout the entire chemical process. If you reverse a reaction, then the sign of the delta H is reversed. So if we look at these 2 bullet points, again, this is basically continuing on with the first few strategies I gave you about the thermochemical equations. If we look at the first bullet point here, it says because delta H of reaction is extensive, you can look at 2 different processes here where you have carbon, which is a solid here. If it combusts with oxygen, it will produce CO2 gas. In this particular reaction, you can have delta H is equal to negative 393.5 kilojoules. What happens if you have 2 moles of solid carbon reacting with 2 moles of oxygen gas to produce 2 moles of carbon dioxide gas? You basically have a baseline of the same reaction from before, which was an enthalpy of reaction that was negative 393.5 kilojoules. But now, since you have 2 moles throughout the entire thermochemical equation, you would take those 2 moles and multiply it by your delta H value, giving you an overall delta H of reaction value for this second reaction to be negative 78.0 kilojoules. Now what happens looking at the second bullet point, what happens if we reverse the reaction? Now we reverse the reaction, that means the product now becomes the reactant. It moves to the left hand side, so you have carbon dioxide gas producing solid carbon plus oxygen gas. The delta H of reaction now becomes positive because you reverse the reaction. So anything that you do to the chemical equation, the thermochemical equation, whether you multiply it by a factor, whether you divide it by a factor, or you reverse it, it affects the enthalpy of reaction, or the enthalpy of the thermochemical equation. So that is critical. Basically, what's about to happen is that each thermochemical equation will be looked at as a math equation now. So if we multiply by 2, we have to multiply our enthalpy by 2. If we divide the equation by 2, we have to divide our enthalpy by 2. If we reverse the equation and it has a plus enthalpy of reaction, if we reverse it, then the enthalpy of reaction will become a negative enthalpy of reaction. So whatever we do to our thermochemical equation, we will have to do to our enthalpy value. So with that being said, now we can go look at a different process for helping us solve these enthalpy of formations or enthalpy of reactions, and we can look at something called Hess's law. So Hess's law is noted as the indirect method of actually doing this. So this should be slide 19. If we look at this and we actually take this example, and again, you should be watching this in the play mode. The problem says, given the following information, we have 2 moles of nitric gas plus oxygen gas that produces 2 moles of nitrogen dioxide gas. We have an enthalpy of formation to be, an enthalpy of reaction to be negative 116 kilojoules. And if we look at the second equation they give us, it has 2 moles of nitrogen gas plus 5 moles of oxygen gas plus 2 moles of liquid water produces 4 moles of nitric acid, aqueous nitric acid, with a delta H value of negative 256 kJ. Lastly, we're given nitrogen gas plus oxygen gas yields 2 moles of nitric oxide gas. This has a delta H value of plus 183 kilojoules. We're asked to calculate the delta H for the reaction below. Keep in mind that the superscript of the degree sign is basically letting us know that this is under steady state conditions. That means that basically you can start at things such as 1 atm, regular temperature to 25 degrees Celsius, 22 to 25 degrees Celsius, steady state conditions. So we can divert back to Chemistry 111 for clarity on steady state conditions. So how do we proceed with calculating the delta H of reaction for the following? What this is telling us is that overall, our final reaction that we're interested in is what happens, or how do we produce 3 moles of nitrogen dioxide gas plus hydrogen liquid to produce 2 moles of nitric acid, aqueous form, plus nitric oxide gas. This is the overall equation, thermochemical equation we're interested in. So what we have to do is we have to orient the 3 equations above to basically solve or appear to be the bottom equation. Okay? So if we continue in play mode and press the down arrow, what you will see, the first step we have to do is write the first equation in a way that we can figure out a way to get rid of or decrease our reactants or our products. So the first step would be to multiply the first equation by 1.5. The second step would be to multiply the third equation by 0.5. And the third equation, we can multiply everything by 2. So when we do that, and we reverse the third equation as well. So we reverse the third equation, So we reverse the third equation. The second equation stays the same. We're multiplying it by 2. The second equation is multiplied by 0.5, and we're doing that in a sense to basically cross out everything that we need to do and that we have and that we don't have. The final equation we're interested in, equation 4, what needs to happen is we need to make sure that from the previous equations above that we cross out everything and have the equations that we need on the left side, or the reactants we need on the left side, and the reactants we need to be on the right side to basically fall in line from the previously 3 equations above. So as we proceed through this and we cancel out everything, our final equation, we can cancel out the 3 moles of nitric oxide, because you have 3 moles NO in the top equation with 2 moles of NO on the bottom equation. You have the N2, the nitrogen gas, on the right side in the third equation, canceling out with the nitrogen gas on the left side in the second equation. We can now cross out our oxygens in the second equations on the left in the reactant side, and then our oxygens on our right in the first equation. In doing that, we will end up with 3NO2 plus H2O liquid produces 2NO nitric acid plus NO gas. Now, we add up our delta H values by simply doing math. So you would simply say plus 174 kilojoules minus 128 plus 183. That should give you a total of negative 137 kilojoules for the overall reaction of 3 moles of nitric oxide plus water produces 2 moles of nitric acid plus nitric oxide gas.